Thank you, everyone. My name is Jianpeng. I'm assistant professor at the Department of Real Estate and Construction in the University of Hong Kong. Today, I'm going to give a presentation. The title is a Scalable Strategy for the Configurator Adoption in Residential Projects. So this is our team. We're a group of researchers, except me, the researchers from the Zurich University of Applied Science and the industry experts from the Implenia. So I would like to start a brief intro. So in the last 25 years, we have seen the IT and digitalization have completely changed the life. And to add to that is the rapid development of AI has shaped the landscape of multiple industries, this including our industry. However, it almost takes the same time to design, construct, and deliver a building project now as it was 25 years ago. So despite this challenge, we see a lot of opportunities. For example, the modular construction has proved to demonstrate a potential of cost saving up to 22 billion, and among which, this project, we are focusing on the multifamily housing project. So to do this, we are going to look at we are going to reconsider the workflow and tools we are using in the current industry. This is and we need to take more authorship in the topic of the tool development. So the digital design tools has a history of over 75 years. We have seen it's gone through the passive drafting tools to generative tools, and more recently we have seen this ecology of the toolkits emerging. Try to enable the data exchange between each of them. However, the interoperability issue between those tools are not well resolved. So this project, we are aiming at to develop a workflow and tool to enable designing with standardized kit or parts so as to promote the application of industrial construction. So we call that the project to product configurator. So this is the basic building blocks of the proposed configurator framework, and we're going to start with the product structure. So this is the classification or hierarchy of the schema of the product structure, starting with the minimum component of the products, such as the gypsum board, and then we have a sub-assembly, like a panel, which could be fabricated in the factory and assembly on site. And then we have a more completed assembly, which refers to the prefabricated 3D module. And all of the above elements which could be combined in different building configurations. This is a video to show you we create a database with building elements which comprise the kit or parts catalog, and each building element which is described with the geometry properties, the maximum and minimum lengths, the physical properties, the structural, the thermal and acoustic properties. And to help the user to browse and edit and select the kit or parts, we also develop a graphic user interface. And the benefit for that is the user, once the user select the elements, they can visualize it at the same time, and or more importantly, they can also download it as the structured data, such as the IFC or JSON file format, which could be used or shared across multiple BIM platforms or on the web. So the next component of this framework is the user input. So users start with the upload a floor plan, which could be in different scale, and the system will interpret the design here. Interpret the design, which means it will understand the geometry of the floor plan and also understand the functionalities of the rooms, and then this would be used as the evidence to do the kit or part selection. And then we do this similarity analysis, and the system will give feedback on the proposed on the uploaded design, whether it is feasible to use, whether it is fit for a prefabrication strategy using the kit or parts in the database. And if not, the system will generate design. And this is the data workflow. The floor plan will be uploaded as a PDF version, and the JSON and the system will interpret the floor plan and output a JSON file format which detailing the geometry properties and the key part selection. This JSON format will be further transferred into IFC for 3D geometry visualization. And this is web application for translating the plans. So user could upload a PDF floor plan and enter the basic information like the floor height, and then the user are able to manually annotate the floor plan, for example, by defining the different rooms, and also they can cluster the rooms by defining an apartment. At the same time, the user can check whether the geometry properties extracted from the floor plan are correct. And the output for this user interface is this graphical interface is the JSON JSON format. And we also test the system with existing design from the modified Swiss dividend datasets, which means we do not need manually annotation on the floor plan. Instead, this dataset gives us a lot of designs which already annotate the apartment. So you can see this already give you the different room types, and this is apartment, 3 different apartments for this floor plan. So they store this information in the CSV file, and the system we use are also able to interpret this file and output a JSON format, and further do the same process to transfer it into the IFC model. And the last component of this framework is the configuration rules. So we are able to support the system to determine which key paths to use. We are going to represent this uploaded floor plan as the graph representation. And in this graph representation or graph structure, the loads represent the rooms and elements, and the age represents the relationship between those nodes, such as the membership relationship to tell you which walls belongs to which room, and also the adjacency relationship tells you which room are next to which room, or which element are next to another element. And then we are defining a set of graph-based rules. For example, these rules could be used to determine the exterior and interior elements, the structure and the non-structure elements, and also to specify for example, the insulation requirements. So this rule could be used to determine could be used to select the key paths from the database. And this is a demo to show you how the JSON and the graph data could be translated into a 3D geometry at its first time, and then to assign the different type of the key parts. The same key parts are shown in the same color. So our next step is to wrap up all the different separate building blocks and to build an integrated web-based configurator. And we expect to see this is a user journey which could upload a floor plan. This could be in different file formats, IFC or PDF or CSV. And then if the user upload an IFC file, the system will check the file to make sure the metadata are correct. And then the user are able to select a specific level and enter the building portfolio, the mix of apartments, and the system will generate various different design using the key parts. From that, the system will output the related project performance, such as cost, energy, and carbon. This is just to show you the user could see the different design alternatives and compare them in different project performance. In the end, the user are able to export it as the IFC file or DWG file for the further processes or the collaboration among other stakeholders. So technically, from technical perspective, what we're doing now is to generate the design alternatives using the key parts. So previously, I showed you how assign the key parts using this rule-based system. But if the system reports the uploaded design is not fit for the key individual parts in the database, the system are able to generate the modification on the existing, on the uploaded floor plan, or to generate a new floor plan. And this lays the foundation for the further comparison and evaluation. So as a summary, what I present today is like a configurator framework, which is scalable and can be adapted to other residential projects. Thank you very much.